Good morning. Today we are going to discuss the analysis of pin joint frames or trusses by direct stiffness method. So as an illustration, I'll see this example. A truss with joints A, B, C, D is carrying two loads 80 kN and 100 kN. The question is to find the forces in members of the truss. Analyze by stiffness method and find the forces in members. So we can assume here one assumption, the first assumption, assume AE, the axial rigidity. Since area of cross section of each member is not given, we can assume A into E is same for all members. So if it is given separately, we can use that area of cross section. Otherwise, we assume the axial rigidity, product of AE is called axial rigidity. It is same for all the members. So to start with, the first step in stiffness method is always identify the degree of freedom or kinematic indeterminacy of the structure. Kinematic indeterminacy is the joint displacements, number of independent joint displacements possible in the structure. In looking into this, here the joint B, joint C and joint D are pin joint or they are at hinge supports. So there will not be any horizontal displacement or vertical displacement. The two possible movements in a truss joint of a truss or node of a truss is two, one horizontal displacement and vertical displacement. There is no rotation. The members being pin connected, they are free to rotate. So the two possible movements per node is a horizontal and vertical displacement. So the only possible movement here is the displacement of joint A. So the degree of freedom is 2. The horizontal and vertical displacement of joint A or the loaded joint. If it is difficult to analyze for that, you can mark down like this. Mark the coordinates of the structure. Joint A, you mark 1 horizontal, 2, the two possible displacements. Joint B, 3, 4. Node C, 5, 6. Node D, 7, 8. You assign the coordinates from all the joints, for all the joints, 1 horizontal and 2 vertical. Similarly, 7, 5, 6, 7, 8, 9, 10 like that. Now out of this, we have the known boundary conditions. The known boundary conditions are D3 is 0, D4 is 0, D5 is 0, D6 0, D7 0, D8 0. So D3 to D8 are known displacements, they are 0. Therefore, the remaining is 1 and 2. So D1 and D2 are the unknown displacements. So the degree of freedom is equal to 2, the horizontal displacement and vertical displacement of joint A. So that is the first step. Now coming to the second step, the element stiffness matrix for the truss in element stiffness matrix in global coordinate direction. Global coordinate direction means we consider that element AB. This is element AB. The angle of this element from the element to the x positive direction, this is direction 1. The node is the displacement direction 1. This is the coordinate direction 2. The second node, it is 3, 4. So for the element AB, considering the element AB, the nodes A and B are the two nodes of it. The coordinates are 1, 2, 3, 4. And the angle theta, you have to always measure it from the element to the horizontal direction at the first node. So I am taking A as its first node. This is the second node. So measure always, this is very important, theta should be measured clockwise from the element towards positive direction of x-axis at node 1. So this is the global direction, global positive x, global positive y, similarly at this node. So measure theta. Once you measure theta like this, if you can calculate theta, then the stiffness matrix for that element, can be written as AE by L, C square, CS, CS square. Okay. Then here write minus C square, minus CS, minus CS, minus S square. This should repeat here. It is minus C square, minus CS, minus CS, minus S square. And this will come here. C square, CS, CS, S square. This is the stiffness matrix for an element with coordinate 1, 2, 3, 4. AE by L into C square, CS, CS, S square. Remember those 4 terms. What is the C square means? Cos square theta. This is cos theta, sin theta. Cos theta, sin theta, sin square theta. So if you calculate theta, I can complete the element stiffness matrix for the first element AB. So looking into the figure, looking into the geometry of this figure, this angle is theta. Let me mark, say this one. This angle with the vertical as say theta 1. How can we find out now? This vertical distance is given in the question 2.4 meter. This horizontal distance is 1.8 meter. So I can easily calculate what is this angle. That is sine theta 1 is equal to length of this side is 3 meter. This side is 3 meter. This is 5, this is 4. So I can calculate sine theta 1 is equal to opposite side 1.8 divided by 3. From that I will get theta 1. Theta 1 works out to 36.87 degrees. Therefore theta, angle from the member to the x positive direction. So this is theta 1 plus 90 degrees. It is 126.87 degrees. Now I can calculate what is cos theta. Cos theta works to 0.6 and sin theta works to 0.8. Therefore cos square theta is 0.36. Sin square theta is 0.64. And cos theta sin theta is 0.6 into 0.8, 0.48. So for the first element, the length of the member is 3 meter. All the values to be filled in this matrix are known to us. Hence I can write the stiffness matrix for element AB is equal to AE by L. Length is 3. C square 0.36. CS CS is 0.48, CS 0.48, S square 0.64. I make everything negative here. Minus 0.36, minus 0.48, minus 0.48, 0.64 with a negative sign. Now similarly here, minus 0.36, minus 0.48, minus 0.48, minus 0.64. Here 0.36, 0.48, 0.48, 0.64. So the stiffness matrix for the first element AB we have obtained. The only thing is to be noted is measure the angle theta correctly. I repeat, from the element clockwise towards x positive direction at the first node. That is also important, at node 1. Now the coordinates are 1, 2, 3, 4. So if you want to assemble it, we should write the coordinate numbers at the top. So we write 1, 2, 3, 4. Similarly 1, 2, 3, 4. There is an AE by L term outside. You divide each term with 3 and rewrite that matrix. Okay, now I have written the stiffness matrix for the first element AB in global coordinate directions. Stiffness matrix for AB in global directions. After dividing with the length of the member, this is the stiffness matrix. Written 1, 2, 3, 4 on the top as well as on the left. Now coming to the second element. Second element is AC. Element AC. So mark the element AC. This is joint A, joint C. The length of the member is 2.4 meter and the coordinates are at the first inch. This is the first node. The coordinates are 1, 2 and the second node it is 5, 6. Measure the angle from the element up to the x positive direction at the first node. This is the first node A. So this is angle theta and that is equal to 90 degree. So for corresponding to 90 degree, you calculate what is cos theta. Cos theta 0, sin theta 1. Hence you calculate cos square theta, sin square theta, cos theta, sin theta. Then write the stiffness matrix. Stiffness matrix for element AC in global coordinate direction is equal to AE by L. AE by 2.4 into C square CS CS square. On completing that, you'll get AE. Dividing by L, I will write the values 0, 0, 0, 0.42, 0, 0, 0, minus 0.42, this should repeat here 0, 0, 0, minus 0.42, 0, 0, 0, 0.42. That is dividing the C square CS CS square divided by this 2.4. I have written this matrix for the second element and the numbers at the top and left to be written is 1, 2, 5, 6. So this is 1, 2, 5, 6. So the second element 1, 2, 5, 6. 1, 2, 5. This is 6. Always A is outside there. Okay, A is outside. So that's the second element. Now coming to the third element. Third element is element AD. This is the position of element AD. This is the direction. Coordinates are 1, 2, 7, 8. So from the element to the x positive at the first node, this is theta. So A, D. Looking into this figure, this vertical distance is 2.4. That horizontal distance is 3.2. The length of the member is 5 meter. So we can calculate what is sin theta. Sin theta is 2.4 by 5. And cos theta is 3.2 by 5. It works out to 0.6, 0.8. So I can write what is C square, S square, CS, cos theta, sin theta 0.48. Now you write the stiffness matrix for this element AD in global coordinates is equal to AE by L. Length of that member is 4. AE by 4. It is 4. 2.4 by 4. 3.2 by 4. Length of that member is 4 meter. So I'll repeat once again for the member AB. Coordinates 1, 2, 7, 8. Length is 4 meter. This is 2.4, 3.2. Sin theta is equal to 2.4 by 4.6. Cos theta is 3.2 by 4.8. Evaluate C square CS square. Then AE by L. AE by 4 into C square CS square. Post it and divided by the length The final matrix will be 0.16, 0.12, 0.12, 0.09. So this place it is minus 0.12, minus 0.09. This has to be repeated here. Minus 0.16, minus 0.12, minus 0.12, minus 0.09. This here 0.16, 0.12, 0.12, 0.09. So this is the stiffness matrix for that element AD, and the numbers to be written at the top as well as left is 1, 2, 7, 8. 1, 2, 7, 8. So now we have written the second step, the stiffness matrix for all the elements. It is very simple. Just remember C square CS, CS H square. Evaluate that 4 terms based on the value of the angle which the element makes with the x positive direction at its first node. So now we have written all the stiffness matrices. Now we have to assemble it and find out the global stiffness matrix, the next step. Okay, next step, the third step is the stiffness matrix in global coordinate directions. So I am going to write it here. Stiffness matrix in global coordinate capital K for the structure, the stiffness matrix for the structure. We know there is only 2 degrees of freedom, that is joint A. There was a note of 80 noted here. So only 2 degrees of freedom, joint A, horizontal displacement and vertical displacement. So we have to apply the boundary conditions in the element itself and delete the rows and columns bearing numbers 3, 4, 5, 6, 7, 8, because the degrees of freedom 3 to 8 are 0. So from the first element, you delete the column 3, column 4, row 3 and row 4. So the remaining is posting will be corresponding to 1 and 2. So post it in the stiffness matrix for the structure. So from the first element, the contribution is at 1, 1, it is 0.11 location, it is 0.12. And the next towards right of it, 1, 2 location, it is minus 0.16. And 2, 1 location, it is 0.16. And 2, 2 location, it is 0.213. So we have entered the elements from the first element after deleting the row and column with numbers 3 and 4. Now coming to the second element 5, 6. So cancel column 5, column 6, row 5, row 6, the remaining element in 1 and 2. You post it there. So from the second element, it starts at 1, 1, it is 0. And 1, 2, also it is 0. 2, 1, it is 0. And 2, 2, it is 0.42. So 4 entries from the second element also we have marked 0, 0, 0, 0.4 in the corresponding locations. Now coming to the third element. The third element D7 and D8 are 0. So we have to delete 7, 8. 7, 8. Delete rows and columns bearing numbers 7 and 8. So the remaining element, these are the 4 elements. Post it accordingly. In the position 1, 1. 1, 1, there is 0.16. To the right of it, 0.12. Below that, 0.12. And next, 0.09. So now we have posted the elements from the 3 elements into the structure stiffness matrix. Added together, this will work out to 0.28. This works out to minus 0.04. This works out to 0.28. This is minus 0.16. first element, it is minus 0.16. From the first element, it is this one is minus 0.16. You remember 0.12 minus 0.16 minus 0.16 0.213. So this works out to minus 0.04. Here it is altogether, it will work out to 0.72. So the stiffness matrix for the structure as a whole is AE into 0.28 minus 0.04 minus 0.04 0.72. See, the stiffness matrix for the structure, we post from all the elements in the corresponding locations and sum it together and we'll get 0.28 minus 0.04 minus 0.04 0.72. It is a symmetric matrix of 2 by 2 sides and the diagonal elements are larger when compared to the off diagonal terms. So next step is the equivalent joint load vector. P is equal to P0 minus PF. In pin joint frames, or we call it as trusses, there will not be any fixed end moment. They are pin connected, they are free to rotate, so there will not be any bending moment. So the fixed end moment vector is equal to 0 for trusses. So the external load vector, the joint load vector P is equal to P0 itself. P0 is vector of externally applied loads at the selected nodes. So in this question, there are two loads at the selected node A, or I can write P0 corresponding to coordinate 1 and P0 corresponding to coordinate 2. This is P0 vector corresponding to coordinate 1. Coordinate 1 is horizontal direction, it is 100. Coordinate 2 is, we have marked the coordinate 1 and 2 like this. This is 1, this is 2. And for the coordinate direction 2, the load is 80 kilonewton, but it is opposite to the direction of 2. 2 direction is upward, the load is acting downwards. So it is 100 minus 80. Therefore, the load vector P is equal to 100 minus 80. Now the next step is step 5. We solve the equation, stiffness equation, K into D is equal to P. So the stiffness matrix, we got it AE 0.28 minus 0.04 minus 0.04 0.72. That into D1 D2 is equal to 100 minus 80. Solving these equations, 0.28 d1 plus minus 0.04 dt equals 100, 0.4 d1 plus 0.72 dt equals minus 80. Solving, we get d1 d2 as 1 by AE into 34.4 minus 92. So these are the values of displacement of joint A. The physical meaning of it is D1 is 34.4 by AE. That means the horizontal displacement of joint A is towards right 34.4 by AE. And the joint displacement, vertical displacement of joint A is minus 92 by AE. That means the direction 2 is upward. So the displacement of joint A is downward. This means the vertical displacement of joint A is downward 92 by AE and the horizontal displacement of joint A is towards right 34.4 by AE. So now we have arrived at the joint displacements also. The final step is to arrive at the forces in members. Now coming to the last step, the forces in members, we have to consider the element AB first. We can have the element AB. It's having length 3 meters and nodes. First node coordinates 1 and 2 and the second node coordinates 3 and 4. The force in member AB is given by AE by L into the first node horizontal displacement is D1, the second node horizontal displacement is D3. So difference in horizontal displacements D1 minus D3 into cos theta plus vertical displacement first node D2, second node D4. So difference in vertical displacements D2 minus D4 sin theta. So this is the formula. The force in member AB at its first node. Actually the force in member at node 1 at the first node is given by AE by L into D1 minus D3 cos theta plus D2 minus D4 sin theta into AE by L. So let us substitute these values. In this particular case, we have D1 and D2. We do have the values obtained from the previous step. We know D3 and D4 are 0. So this D3 is 0 as well as D4 is 0. So this is actually, if it's a single joint truss, it is easier one. AE by L into D1 cos theta plus D2 sin theta. So AE by length of the member 3 meter, D1 the value is 34.4. Cos theta value we have arrived from the first step in the while forming the element stiffness matrix. Sorry, it is not 34.4. It is 344. It is 344. It is 344. Cos theta value is minus 0.6 for the first element. And D2, the D2 value is minus 92. Minus 92. And the sin theta value for that element is 0.8. And these displacements are 1 by AE. This AE gets cancelled and you get the answer as minus 93.33 kilonewton. This implies, if the answer is negative, it implies it is a tension member. The answer is negative, it implies it is a tension member. Now coming to the second element, force in member small PAC, force in member AC. Since the element I am marking small p, force in element AC will be first element force AE by L. AE by L. AE by L is 2.4. D1 minus D5. D1 minus D5 cos theta plus D2 minus D6, second vertical displacement, sin theta. Here also the D5 is 0, D6 is 0. These two displacements of joint C is 0. So we can write it as AE by 2.4 into D1 344, and cos theta of that element was referring to the first element stiffness matrix. It is 0 and D2 minus 92 and sin theta is 1 into this 1 by AE. So it gets cancelled and we get the force in member as minus 38.33 kilonewton. That means that is also tension member. Now coming to the third element, force in member AD is equal to AE by L D1 minus D7. D1 minus D7 cos theta plus D2 minus D8 sin theta. Substituting the values, this is also 0, also D1, D7 0, D8 0. Substitute the values of cos theta and sin theta from the first step. We get the answer 55 kilonewton. This is positive, so that member is subjected to compression. So we have got the values of the member forces. Minus 93.33 means member AB is tension. Now we have to mark it in this original figure. Member AB 93.33 tension. Tension is a force which pulls the joint. So joint A and B, draw arrows away from the joint and mark the force 93.33 kilonewton. Second member, the force is minus 38.33 tension. So mark tension is the member. It is 98.33. For the third member, it is compression. Compression means it pushes the joint. It is 55 kilonewton. So after completing the analysis, mark all the forces in the figures or you tabulate it. Remember the numerical value of the force in kilonewton, tension or compression. So the best way is to express it in the pictorial representation. So thus we have come to the end of the analysis of pin joint frames, or otherwise called analysis of trusses by direct stiffness method. Thank you.